Alright guys, welcome to this page of the notes, and what we're going to do here is kind of begin to introduce some postulates, alright, some postulates, and we will talk more about postulates when we kind of get to the idea of proofs. One of the unique things about geometry is that we're going to use this idea of proofs in order to justify. All right, in order to say, here's why I can do something. And that's kind of what distinguishes geometry from algebra. And I don't want to say too much about it too soon because I don't really want to steal my own thunder. But really kind of the idea is in geometry, you sort of follow an order of steps in order to solve a problem. Okay, so if I give you an equation, right, and I ask you to solve for a variable, you go through a process of steps, maybe adding and subtracting things from one side or the other, or multiplying and dividing things from one side or the other. You may have to factor or distribute or something like that. It's sort of an order of steps in order to arrive at your solution where you have solved for the variable. And we're going to do algebra in geometry. In fact, I'm also an algebra teacher, and so every opportunity I get, we're going to do algebra in geometry. I'm going to do as much of it as I can. I want you to see the connection between the two. However, there is a very big distinction between the two, and really that distinction comes here. This idea of postulates, theorems, and sort of definitions. Definitions, postulates, and theorems. In geometry, unlike with algebra, you will be given many times a figure or a diagram. And in order to arrive at, I don't want to call it a solution because it won't always be a solution, but in order to arrive at an answer, okay, in order to answer the question they're asking you about the diagram, in sort of working your way through a series of steps, a process like you might think of in geometry, instead, you may have to apply definitions, postulates, and theorems, which we'll talk about here a little bit now and definitely much more later, to sort of help you work your way through that diagram or figure. And I know right now that that sounds really ambiguous and might be kind of hard to understand what I'm saying. I promise, just give me some time as we work our way through this course. You'll see exactly what I mean, and I'll try to point this out to you as we go. But please do not think that geometry is just like algebra. Yes, we're going to do algebra, and I'll do it as often as I can, but geometry is really sort of a very different animal. And it's because of this idea of needing to use definitions, postulates, and theorems to justify our steps, in order to justify why we're doing what we're doing. Now, that's more than enough on that for now. We'll come back to it later. The idea of postulates for now, the only thing that you need to know is that a postulate is a statement that does not need to be proven. You could also think of postulates as an axiom. If you are familiar with the term axiom, if you're not, don't worry about it. I won't ever use the term axiom. We're going to call them postulates in geometry. But it is a think of it like this. It's a statement that is common sense. Right? It doesn't need to be proven. That's the way that things are. And I'll give you a perfect example here in just a second. So postulates, statements that are known to be true. You don't have to prove that they're true, okay? Theorem are statements that must be proven. You would have to prove a theorem. Postulates you don't have to prove. Postulates are kind of common sense things. Theorems are something that are maybe not quite so common sense, things that you would have to justify as being true. And here's a great example. I have the ruler postulate. The ruler postulate. And as I go through it, you can be like, yeah, no duh. That's exactly the point. That's the idea of a postulate. It's kind of that stuff that's like, duh, yeah, that's just the way things work. Exactly. You understand then what a postulate is. It is a common sense statement that is just known to be true. You don't have to prove it. So we have the ruler postulate. Now I've got a bunch of words here, but essentially here's what the ruler postulate is saying. If you are given 2 points, A and B, the ruler postulate says you can measure the distance between those 2 points. That's it. That's the ruler postulate. Okay? You don't have to prove that you can measure the distance between 2 points. Grab a ruler, drop the ruler down, right? Start at point A, measure to point B, and you can find that distance. Now, apply your own units. If the points are really far apart, maybe you got to use meters or miles. If the points are closer together like this, you could use inches or centimeters, right? We won't discuss the units at this point. All we're saying is that it is possible to measure the distance between any 2 points. Because that's a postulate. That's a common sense, yeah, no doubt. You can measure the distance between 2 points. Got it. Perfect. That's what postulates are. So as we go through this course and I give you postulates, we're not going to prove them because they don't need to be proven. They're common sense things. And so there's our ruler postulate. Now, from that ruler postulate, what we're going to do is get something else. What's known as the segment addition postulate. And again, this is going to be something when I explain it to you, you're going to be like, yeah, of course. That's the way it works. Fantastic. So here we go. The segment addition postulate. Here's what we're going to say. If you have 3, very important, collinear points, meaning these points, you must be able to connect these 3 points with a line. Collinear. They're all in a straight line. So I have point A, point B, and point C. In fact, I don't know that the points are drawn on there. So let me go ahead and put those points on there. There's point A. Oh, no, that's not where I want it. That's not where I want it. I want it right there. Point A, point B, point C. All right, so I've got 3 collinear points, A, B, and C. Here's the segment addition postulate. And guys, again, this is very common sense. That's why we call it a postulate. It doesn't need to be proven. You just know that it's true. Here's what it's saying. This segment, AC, the distance from point A to point C, all right? As long as, and again, this must be true, all right? And it just makes sense. B must be between point A and point C. If B is outside of point A or point C, then this postulate doesn't apply, and you'll see why. But I've got this line segment, AC, or this distance from point A to point C, this distance right here, is equal, right? That's exactly what I'm saying, is equal to the distance from A to B plus the distance from B to C. That's it. That's the segment addition postulate. You can measure a bigger distance if you know the sum of the smaller distances that make up the larger distance, right? I could divide this into as many different smaller pieces as I want to. As long as they're all smaller pieces of the greater distance, add them together, you can get the greater distance. That's the segment addition postulate, okay? Point B, just remember that point must be between my endpoints though, okay? If B were out here, right, then the segment addition postulate wouldn't apply because you're not then adding the segments. It's extended beyond the segment that you're trying to measure. I know you can clearly visualize what's going on there and why that wouldn't work. So as long as B is between my 2 endpoints, A and C, add up the smaller segments to get the larger segment. Okay, this is the segment addition postulate. Here's the converse. Here's another way of saying it that means the same thing. If AB plus BC, so AB plus BC is equal to AC, so the 2 smaller parts added together equal the bigger part, then B is between AC. Right? So this is going to be a good way of, instead of B being between AC and using the segment addition postulate to find the distance, if I tell you the segment addition postulate applies, then you know B must be between the 2 points. Again, we'll talk about this way more, but this is actually what we call a converse. A converse statement. This is the segment addition postulate. This is the converse of the segment addition postulate. What we've done is we've just simply switched the 2. If B is between A and C, then segment addition postulate. If segment addition postulate, then B is between AC. See how the parts have kind of switched places? Here's if B is between AC, then segment addition postulate. Look at how they've flipped places. If segment addition postulate, then B is between AC. See how those 2 things, right? Those 2 statements have kind of flipped, right? We'll talk more about it later, but this is what's known as a converse. Segment addition postulate, the converse of the segment addition postulate. You just take that statement and have those guys switch places, and you get this converse statement. Now, we'll talk about the actual validity of converse statements later, so don't worry about that now, but just kind of a brief introduction to when I say converse later on, you already know what I'm talking about. Here we go. Let's try a problem. And again, draw pictures. Love, love, love pictures. Here's what we've got. I want you to find BC if B is between AC. Fantastic. Here we go. Boom. There's A. Boom. There's C. There's my line. And I tell you that B is between AC. Where between AC? Doesn't matter. Put it wherever you want. I'll put it right there. There's B. Here's what I tell you. I tell you AB is 2x minus 4. So 2x minus 4 is that distance right there. 2x minus 4 is that distance right there. Then I tell you BC. BC is 3x minus 1. That's that distance right there. Right, just putting little arrows in there. Again, the point is this. This distance right there is 2x minus 4. That distance is 3x minus 1. Here's what I want you to do. Actually, we're not done. Careful, read the directions. And AC is 14. Check this out. From A to C, the distance, boom, is 14. I want you to find BC. Okay, so here's what we're going to do. I'm going to set up, right, you can see, looking at this, using the segment addition postulate. Here's what we're going to do. We know that the segment addition postulate says the segment AB, that segment, plus the segment BC is equal to the entire segment AC. All right, so the segment AB plus the segment BC, segment addition postulate, add those two segments together, I get the total length. Go ahead, plug in everything you know. I know that AB is 2x minus 4. 2x minus 4. Plus, what is BC? Well, it's 3x minus 1. As promised, every opportunity I get, we're going to do algebra. Here's our first case. AC, the segment AC is 14, so that's all equal to 14. You're going to go ahead, solve for the unknown. Find x. How do you do that? Well, really simple, right? Go ahead and combine like terms. 2x plus 3x, that's 5x. I have a negative 4 minus 1, that's going to be a minus 5. That's all equal to 14. I need to get the x right. Solving means isolating the variable. Add the 5 to the other side. 5x is going to be equal to 19. That's adding 5. Why add 5? Well, it's a minus 5. So how do I move it to the other side? Since it's a negative 5 here, add it to the other side. That'll move it to the other side. And then divide both sides by 5, right? That's multiplication. It's 5 times x. How do you undo multiplication? Well, divide both sides by 5. So x is equal to 19/5. Please be very, very careful. Yes, I am going to do this, and it is not purposefully to try and trick you. That is not the purpose. But you do need to be aware that you need to read directions very carefully. In this problem, did I ask you to solve for x? No. But all of you are coming to me from Algebra 1, or you're taking this class or watching these videos after taking Algebra 1. Most students go Algebra 1, Geometry, then Algebra 2. You're coming to me from an algebra class where, in algebra, your final answer was generally the solution that you get when you find x. And so please do not fall into this trap, all right? Because it's easy to do, and you need to be very diligent to think about the problem, all right? You find the value of x, and most of you are going to go, boom, there's my answer. Cuckoo, cuckoo, I'm done, on to the next one. And you're wrong. That is not your answer. That is not what I asked you to find. I did not ask you to solve for x or find the value of x. I asked you to find this distance, the line segment BC. So what do you need to do? Well, go back and plug it in. You know that BC is equal to 3x minus 1. But we know what x is. X is 19/5. So BC is equal to 3 times 19/5 minus 1. Okay guys, we are going to use fractions. Fractions are going to be all over the place. I love fractions. You should love fractions. Fractions are friends. Fractions are our friends. You can use a calculator if you want to. I won't ever use a calculator. We're just going to sort of go through, show you how to do these guys, right? But in order to multiply these, right, I have 3 times 19/5, which means the 3 gets multiplied into the numerator. Boom. So BC is equal to 3 times 19 is 52. All over 5 minus 1. So this is 52/5. 52 divided by 5, multiply that 3 into the numerator, keep the denominator. 52 divided by 5, or 52/5 minus 1. You could certainly subtract the 1. In fact, we're not certainly could. We are going to subtract the 1. Line segment BC. 52, I'm sorry. No. Scratch that. 52/5 is my final answer. That is 57/5. Sorry, I apologize. Sometimes I make those, I get going too fast. My brain's going ahead of where I am. I apologize about that. 3 times 19 is 57. If you were using a calculator and checking my work, good for you. So 57/5 minus 1, subtract the 1. 52/5. Again, just a quick note about this. You absolutely could use a calculator if you want to, but please remember the way that it works when adding or subtracting fractions. You need a common denominator. 57/5 minus 1 means I need that 1 to be over the common denominator, which in our case is going to be a 5, right? I need both of those guys to be to have a 5 in the denominator. But remember the way algebra works. I can't just put a 5 down there. If I put a 5 in the denominator, I also have to put a 5 in the numerator. Which means, right, that this guy right here, -1, is the same as subtracting 5 over 5, right? 1 times 5 is 5 over 5. So another way you could think of this guy is as 57 over 5 minus 5 over 5. In which case then 57 minus 5 is 52, and you keep your common denominator, right? So adding or subtracting, you must have a common denominator, but you can't just put that number in the bottom, right? That's not the way algebra works. Algebra is all about balancing. Think of algebra almost as like a set of scales. And if you add something to one side of the scales, you must balance it out. Algebra is all about equality, right? I've got two things that are equal. If I add something to one side, I've now lost my equality. And that's not okay in algebra. That's not okay. So in order to maintain equality, I have to add something to the other side. If I subtract something from one side, I've lost my equality. So algebra says to maintain the equality, if you subtract something from one side, subtract it from the other side so that equality is maintained, right? So think of it as like a set of scales. Same thing, if I multiply one side by something, you have to multiply the other side by the same thing. Fractions work the exact same way. I multiplied a 5 into the denominator. I now no longer have equality, but I can fix it if I multiply the top by 5 as well. Now I've maintained the equality. So you can't just put a 5 in the bottom and walk away and say, done, I did it. No, that's not the way algebra works. You've got to keep those scales balanced. You have to maintain that equality. And so you'll multiply a 5 in the top as well. All right, guys, so two postulates, the ruler postulate, the segment addition postulate, they don't need to be proven. These are statements that are just known to be true. They're common sense. We don't have to prove them. And we can use these postulates to help us solve problems in algebra. The only reason that I could set this up and then do the algebra is because of the segment addition postulate. That postulate allows me to say, hey, if I add these two things together, it's got to be equal to this guy. I can do that because of the postulate. If you didn't know the postulate, you wouldn't be able to write this statement, and then we couldn't have answered the question. And that's where geometry is going to be a little bit different than algebra. In algebra, you would have already been given this, right? Think about it. This is the algebra. This is what on a quiz or a test or a worksheet, you're given this. I ask you to solve for x. In geometry, we make you go one step further, right? I give you a diagram or a description. I didn't even give you the picture. We drew the picture. I give you a description and I ask you to find something, right? And in order to make this problem work, what did you have to know? You had to know the segment addition postulate to write your own equation, which we could then use to find our answer, which is right here. All right, so hopefully what you guys can now see is kind of some of the difference we're going to deal with when doing geometry, all right? Yes, there's going to be a lot of algebra. I love algebra. We're going to do as much of it as we can possibly do. But to get to the algebra, we're going to have to use things like definitions, postulates, and theorems to help us take that description or take that figure, right, and get ourselves to a place where we can then use the algebra or the information we've been given to arrive at our answer or our solution. And that's really what makes geometry just so wonderful. It's just taking what you guys have already learned and going one step further, one step deeper, kind of developing our understanding. Really excited about it. So we're going to try some more of these. Head on over to the next page of the notes. I'll meet you guys there.